Hello and welcome to our lecture 10 of VLSI design, and this is the continuation of ID equation derivation. And if you want to cover the first part of ID equation derivation, it is episode 9 or lecture 9 in the playlist. I'll add all the playlist and previous lectures in the description. Make sure to click on it in order to understand lecture 10. So we are into ID equation derivation, okay, and this is what we have covered so far. Okay, the last equation, ID equation, that we derived, that was equation number 7, and we had ID equals to mu n cox w by l vgs minus vt, and the whole thing was multiplied by vds, where mu n cox is kn dash and Kn is mu n cox into W by L. That is why I have arranged the curly braces in that manner. W by L is also known as the aspect ratio of a MOSFET. Okay, where W is the channel width, L is the channel length. VGS minus VT is our overdrive voltage, also depicted by VOV. Okay, and VDS is VDS, that we are applying at the drain end. Okay, so Kn dash is process transconductance parameter, and Kn is the MOSFET transconductance parameter. Okay, and the last thing that we did in our previous class was we also observed that the operation of a MOSFET, it behaves as a voltage controlled resistor. Okay, so this was what we did by the end of our lecture 9. Okay, now let's continue from here, because I had told you that kahani abhi baki hai, the story is still left out. Okay, we have to complete the ID equation derivation. Okay, now first thing that we need to note down is, at small values of VDS, channel behaves as a linear resistance, and its value is calculated by VGS minus VT. Okay, so at small values of VDS, the channel behaves as a linear resistance and its value is calculated by VGS minus VT. How can I directly come to this point? This point I can directly come because when I was discussing the application of VDS in previous lectures, where we started off the discussion on the MOSFET physics. Okay, first we had no gate voltage, so at that point how did the MOSFET behave as? Then we applied VGS, then we enhanced the channel, okay, where we got the channel and we made VGS minus VT and all that. Then the third point was what? Application of VDS, where we started off with small positive voltage, right, at the drain end. So when we were giving, at that point what was happening? The current started flowing, isn't it? So when current starts flowing, that means what? There will always be a resistance involved. Without resistance you can't have anything, right? So that is how we can come to this point. Okay, so whatever we have discussed earlier on the topic application of VDS, so from that point we can say this. All right, now the second point would be that this resistance, okay, this linear resistance, due to the application of small values of VDS, okay, this resistance decreases as VGS is increased well above the threshold voltage, that is VT. Okay, but of course if you keep enhancing your channel, if I keep enhancing my channel, this is my channel, all right? Okay, this is my channel L, and if I keep enhancing, means if I keep this VGS is too great than VT, okay? Let's suppose our VT is 5 volts and I am providing VGS as 15 volts. So my VGS is too great than VT, the amount. So what will happen? More number of electrons will be jumping to form the channel, isn't it? More number of electrons will be there. If more number of electrons are there, that means what? When you apply VDS from the drain side, what will happen? The electrons will start moving and the current will start moving in the opposite direction. Okay? Okay. So, if I make this VGS minus VT as at a higher amount, my resistance will obviously drop. Okay? So, this also we have discussed in our previous lectures. Now, then as VDS, if we keep on increasing, what happened? The last thing, the channel tapered. Remember the channel tapering, channel length modulation, pinch off. Okay, so the channel tapered, and because of this, resistance increased. At which side? At the drain end. Okay, because of this, the ID versus VDS graph no longer remains a straight line. Okay, and it takes a bend. Okay, because of this channel tapering and resistance increasing at the drain end, so what will happen? The ID versus VDS graph, okay, will no longer remain a straight line and it will make a bend. Okay, so which ID versus VDS graph am I talking about? In our previous class, you must remember that we discussed a graph, okay, like this. I hope you remember this. If you don't, no worries. I'll attach all the playlists in the previous classes and you can check it out. Okay. So on the y-axis we have the current and on the x-axis we have VDS. Okay. This blue line that is touching on the x-axis, okay, that is touching the x-axis. This line is when VGS is less than equals to VT. Okay, so at that point we will have no current. See this blue line, the first line is actually what? On the x-axis, that means the value on the y-axis will be what? 0. So at this point we have 0 current. When do we have that? When VGS is less than VT. Okay. Now, what is this first thing? At this point, it is, let's suppose VGS is VT plus 0.5. Let this be VGS equals to VT plus 1 volt, okay, and VGS equals to VT plus 1.5, VGS equals to VT plus 2, VGS equals to Vt plus 2.5 and so on and so forth. So this graph we had covered. Okay. So now this is the straight line I was talking about here. Okay. These are all what? Straight lines. Okay. These are all what? Straight lines. So till this point, till which point? Before increasing the VDS. Okay. Before doing this, our graph was a straight line. When we have increased our VDS, due to which channel has tapered and resistance has increased at the drain end, what is happening? That this graph no longer remains a straight line and it takes a bend. Okay, so now let's see what kind of bend we will see in this. Okay, so let's see this graph. Okay, and see here I am taking multiple values of VGS minus VT. Okay, but in this, the graph that we are going to see now, I'll take one value of it. Okay, so multiple graphs I have taken in the previous one. Here I am taking one. So let us see what we have got over here. So till my VDS was what? Not increased beyond a certain amount, it is remaining a straight line. And if I have, let's suppose I have VGS that is less than VT, then what will happen? Okay, so I have plotted two things. Of course, the one that I am plotting over here, this part, okay, this is when our VGS is less than VT, so no amount of current. Okay, so I'll mention who is what. So y-axis is ID, x-axis is VDS. Okay, now I'll just drop a marker. Okay, I'll just drop a marker over here to show that from this point onwards I will show the VDS, what happens to the graph when VDS is increased beyond a certain amount of point. Okay, now this will also extend. Okay, so till this point it is a straight line, and you see, like, it is dependent on the voltage also, and depending on that I am getting my output, that is current as well. So I can very well say that this is my linear region of the graph. This is where my MOSFET is in its linear region. Okay, so why this linear region? How can I say it's a linear region? If you would have studied Ohm's law, which I'm sure you have, because that is the first thing you study in physics. Okay, so you will understand that there is a direct proportionality of current and volt, where voltage is your input and output is your current, and the proportionality is because of the resistance. Alright, so now this is our linear region. Our graph is in linear region. Okay, now I have increased VDS. What if I have increased VDS? Okay, so now what will happen is this graph will take a bend and become a constant value. Okay, to show this properly, it will be like this. So in our linear region, what was happening? our value was increasing, my current value was increasing with increased voltage. Okay, for 1, this, let's suppose this is 2, for 2, let's suppose this is 3, for 3, let's suppose this is 4. Okay, so my values were increasing, hence the name linear region. Now when I'm increasing the VDS, see x-axis is VDS, right? So this is all VDS only. Okay, so if I'm increasing beyond this point, what is this point now? It is of very much importance now. So this point is VDS is equals to VGS minus VT. Okay, if my VDS value is equals to VGS minus VT, okay, so at that point it will make a bend. So the graph bends over here. Okay, the graph bends over here, and if I keep increasing my voltage beyond this point, beyond this VGS minus VT, so what is this VGS minus VT? It is nothing but VOV. Okay, it is VOV. So at this point, my current equation, what is the current value over here? It is a constant. For this value also it is a constant. For this value of voltage is also constant, constant. Okay, so my current moves into a constant value. Okay, so this region is called the saturation region. Okay, this region is called the saturation region, and this region, this point, okay, just before the saturation, is also known as triode region. Okay, so linear, saturation, covered. Okay, there is 3 regions of operation for a MOSFET, and the last region is this part. What is this part? Cutoff region. Okay, this is a cutoff region. So how many regions of operation in a MOSFET? It is again a 2 marks question. Okay, regions of operation in a MOSFET. So first is cutoff. Why first is cutoff? Why not linear or saturation? Because at this point your MOSFET is turned off. Okay, it is not on. So if MOSFET is off, it is MOSFET off, right? Because it is less than VGS is less than VT. So you don't have a channel, you have no electrons, you have no current. So MOSFET is turned off. So no ID. So there is no current itself. So that is my first. Second is linear. Okay, second is linear, wherein we have ID and we have VDS less than VOV. But of course, third is saturation, wherein VDS is increased beyond this VOV, and so in linear region what was happening? Current was growing. Okay, current was increasing, and over here in saturation what happens? ID is a constant value. Okay, ID is a constant value. So if in your VLSI lab Viva They will ask you this question. Okay, so again this is a 2 marks question. Okay, it is a 2 marks question. So these are the 3 regions of operation. Okay, now, and when you are going for the ID equation derivation question in your semester, at that point you have to have this graph, you have to have this graph, both, and all of them should be drawn neatly. If you can't draw a straight line, take a scale with you, take a ruler with you and do it. Okay, now let us get back to our derivation. Yeah, it is not over yet, so I understand. Okay, so now from which point we will start? So we left off where my channel got tapered and resistance increased. So this was the last point we had discussed. Okay, so we will start from that point. So charge in a tapered channel. Okay, so till this point we have discussed only charge in our channel. But my channel has tapered, so of course there I should also see what is the charge in our tapered channel. This charge in our tapered channel is directly proportional to the channel cross sectional area. Of course, whatever is my cross sectional area of our channel, tapered channel, on that only the charge will be directly proportional to. Okay, so this basically means, in a layman's word, if see this, these are all technical terms. Okay, but if I want to understand it as a layman who has nothing to do with VLSI background, okay, so for me, how will I understand this? If suppose I have an auditorium, I book an auditorium and the capacity of that auditorium is 100 people only, including the speaker. Let's suppose we do a meet and greet. Okay, so I book this auditorium and that means it has a capacity of 100 people. So I will take myself into account, that is 1, and then there will be 99 of you that will be able to adjust themselves within this auditorium. Okay, now let's suppose the capacity is 100. Okay, our subscriber count till now, till today, it is 75, hoping that we reach 500 marks very soon. So yeah, spread the word, get your friends to subscribe as well, get your relatives to subscribe as well. Let's do this road to 500 subs. Okay, okay, and if you're watching this video, you are constantly coming to learn from me and you haven't subscribed, please do that. Okay, so yeah, let's get back. So let's suppose the first scenario is what? Me and 99 of you. Okay. Second scenario, capacity is still 100. I am there and the current count is 75. So 75 of you, will there be any problem? No. In fact, it will be okay. 100% capacity, 76 are occupying. That means we still have room for oxygen. Okay. Third scenario, where we have got this 500 subscribers with us. Okay. And I booked, there was no other auditorium left and I'm trying to do this with this 100 capacity auditorium. That means what? If 500 of you turned up also, okay, all of you are very attentive, all of you are very loyal to me and my channel. So me and 500 of you in this room, what will happen? We'll die, right? Okay, we'll die of suffocation. Okay, so depending on the amount of space we have, that much people only we can fit in. Na? This one will never happen. We can't do this. Okay, this is the good example, that actual practical example. But if I have 100 capacity, that means what? I can adjust 1 and 99 of you. me and then 99 of you. So the charge in the tapered channel. So tapered channel means what? Remember this cross section that I was doing? This is our tapered channel. On this side, the size of our channel is still the same. But on this side, the length of the width of the channel will be what? This side it is lesser. Okay. This was our tapered channel. So that is why the amount of charge earlier that it could have occupied, okay, this will be more than this. So the charge in a tapered channel is directly proportional to the channel cross sectional area. Okay. All right. So let us see what is this cross sectional area we have got. Okay. So this will be half of VOV plus VOV minus VDS. Now you're like, oh my god, from where did we get into this now? How did you get to know this? That also I'll show you, no worries. So consider this diagram, okay? On this side it is source, on this side it is drain, okay? And I have told you that VGS minus VT is applied from the gate, okay? What is this VGS minus VT? This is nothing but VOV. And from the drain side we have applied VDS. And because of this voltage drop that happened because we have applied VDS. So before applying VDS, what did we discuss? That the voltage drop across this was VOV only, because only one voltage drop is there, only one voltage is there, so that will be prevalent. Now, the moment we apply VDS, so there will be a voltage drop because there is two voltages taking space now. So on the source end it will still be VOV, and on the drain end what was the effect of this? VOV minus VDS. So we have got the source end VOV and drain end VOV minus VDS. So we have got two voltages on two sides. So what is the cross sectional area? Average. So that here what will be the voltage drop? It will be the average of these two. So from two voltages, so basically it is VOV plus VOV minus VDS, two sides divided by 2. So this is what I have written over here. Okay. Now this thing. So our charge in tapered channel is directly proportional to what then? It is directly proportional to VOV minus half of VDS. See how this one? It will be 2 VOV minus VDS by 2. So if I separate these two, I'll get VOV minus half of VDS. Okay. See, this is the explanation. Okay. This is the explanation. When you are deriving from this point, you will directly jump to this point. Okay. And you will write a statement explaining what has happened. Okay. So, voltage drop along the channel to vary linearly with an average value of half of VDS, okay, at the midpoint of the channel. So basically the statement means what? We have VOV, we have VOV minus VDS, and we understood that it is VOV minus half of VDS. So at the midpoint it is actually half of VDS. Okay, on both the sides we have VOV, right? So at the midpoint it is half of VDS. Okay. Therefore, the relationship between ID and VDS can be formed by replacing VOV by VOV minus half of VDS. Why we are doing this? Because our channel tapers. Our channel will taper the moment we increase our VDS, and we saw the graph of it also. So it is only correct thing that we replace VOV by this average value, the cross sectional area, isn't it? Only then we will be true to our equation. Okay, so that is why we are doing this. So our ID equation will be ID equals to Kn dash multiplied by W by L, VOV minus half of VDS and multiplied by VDS. So this forms our equation number 8. Okay, this forms our equation number 8, where Kn dash is equals to mu n Cox. Okay, now in equation 8, as VDS is reduced, we can neglect the half of VDS term that we have written in equation 8 relative to VOV. See, in this equation we have got two VDS terms. One that is the getting multiplied with the whole equation, and the other that we have currently introduced in equation 8, that is half of VDS. So let's suppose I am decreasing VDS. Let's suppose, okay, if we are decreasing VDS, which term will be lower comparatively? This will be lower or this will be lower? Of course this will be lower. Half of what? Let's suppose from 10 volts of VDS I am making it 5 volts. So already I have halved it. So this one will be 5, this one will be 2.5. And what about the VOV? Relatively VOV will be greater than 2.5 only, because I have to keep my VGS greater than VT. Okay, so when we will be decreasing VDS, because we have to keep fluctuating our VDS to understand our MOSFET. Okay, so at that point we can ignore this part, but not this and not this. Okay, this is what this statement means. This is what the statement means. Alright. And when we do that, when we reduce the VDS, so half of VDS will be neglected, it is even a smaller value. So at that point, what will happen? If we do that, our equation 8 reduces to equation 7. Okay. Now, again, the average voltage along the channel is what? Half of VDS. Here we discussed this one at the midpoint. Okay. Half of VDS. This average voltage gives rise to channel charge and hence to ID is no longer dependent on VOV, but it is dependent on VOV minus half of VDS. So because of the average voltage drop along the channel is half of VDS, this gives rise to channel charge and hence ID is no longer dependent on just VOV but on VOV minus half of VDS. This is just the English statement of what we have done over here. Okay, so no need to get confused. Okay. Now, this implies ID equals to mu n COX into W by L VOV multiplied by VDS minus half of VDS square. This is again the same equation 8. Simply what I have done is I have multiplied this VDS within the bracket and I have expanded my Kn dash. Okay. Nothing more I have done. Simply I have multiplied this VDS, brought this VDS inside. Okay. So now I can write ID equals to Kn into what is VOV? VGS minus VT, that is multiplied with what? VDS minus half of VDS square. Okay, half of VDS square. Now I can simply, if I will like to rearrange this equation now. And if I rearrange it in this manner, that is ID equals to Kn big square bracket within which I will have my VGS minus VT minus VDS by 2 and I am taking my VDS again back to the outside. This equation, that is equation 9. Okay, this equation 9 is the current equation for the linear region. Okay, now, so this is my linear region ID value. Okay, now this is, so we have what? 3 regions, right? Cutoff is ID equals to 0. For linear, we just found it out. Then we have to find out for a saturation also. Okay. So when do we move into saturation region? When I have my VDS that is equals to VGS minus VT. at this point my MOSFET will drive into saturation. So at this value my MOSFET drives into the saturation region. Okay. So what will be my current equation? It will be ID sat is also in the subscript, okay, equals to half of mu n cox W by L VGS minus VT whole square. So this forms our equation number 10 and is the current equation for saturation region. Okay, and at the end simply I'll write down the regions and ID. Okay, first is cutoff. What is my ID value? 0. Second is my linear. What is my ID? It is mu n cox W by L VGS minus VT minus VDS by 2 multiplied by VDS. Okay, multiplied by VDS. Okay, multiplied by VDS. Whenever you are writing down the current equation, don't write kn dash and all those things. Write all the terms mu n cox W by L, then this. Okay, because people like me will question you, what is this kn, why did you write kn dash, why not the whole thing expanded? When you are deriving an equation, write everything down. Okay, yes, I am that person. Yeah. So saturation region, what is my ID? So my ID is ID sat, which is equals to half of mu n cox W by L VGS minus VT whole square. Okay, so these are the three different regions and their corresponding current equations and current values. Now, at the beginning or in the thumbnail itself, you have seen that I have written something called the twist. So what is this twist that I am talking about? The whole derivation that we did today, we kept on talking about tapered channel. And we know once it is tapered, if we keep on increasing VDS beyond this point, what will happen? Channel pinch off. When channel pinches off, at that point what happened to our channel? There was no connection at the drain end. Our L became L dash and the difference is delta L. So our channel length reduced. There is this portion, there is no electrons left, means depletion region. If it is depletion region, means what? In this region we have no electrons. No electrons means no current. No current means infinite resistance. But we are seeing that we have the MOSFET in saturation region and we are getting the maximum current at the saturation region. How is it maximum? Look at the graph. Look at this graph. Till this point it was this value. But when it is in saturation, it is giving me the max. I am getting ID max. Whatever is the maximum value for this MOSFET, like for this VGS minus VT, I am getting the ID max when my MOSFET is driving into saturation region. But my channel tapers and my channel pinches off, and there should have been a infinite resistance over there because we have moved into depletion region. Then how is this possible? We'll see that in our next class. Okay, so stay tuned for lecture number 11. It's going to be very interesting. And subscribe, be my tribe. Okay, spread the word. Let's hit that road to 500 subscribers. Okay, let's hit that. Till that point, that's it for today. Stay happy, stay updated.